Cisco Certified Network Associate Day 18. Welcome back everybody, I'm Imran, Rafai, your trainer for this entire series. Today we're going to look at routing basics, right? And if you guys are following my video series from day 1 and you have gone through the series and reached day 18, you would have at this point learned the basics of switching, right? Now we're going to the next device, right? So if you know Cisco RNS, R stands for router and S stands for switches. So we have completed the basics of switching in the previous videos, and now we are starting to go into the other device, which is a router. And this series will now start moving into the routing topics. In this particular video, we will not be talking about Cisco routers, but we would be looking at the concept of routing, right? So without wasting much time, let's get straight into today's class. Right, so 3 things. We will look at a review, we will look at what we already know, and we will try to fit the router into the knowledge that we already have. So we understand how a router and a switch fits together. So we will have an understanding. So that would be what review would do. And then we will then look at what routing itself is. So we will understand what routing means and how routing works. And then we will look at the types of routing there is in this world, right? So we'll get into review like we said. So this is a topology we had earlier looked at in one of our switching videos, right? So we will look at the data flow, we'll look at how data flows through the network, and we will go back to doing a 3-way handshake, right? The first packet or the first frame that is sent for a TCP 3-way handshake is a sync message, yeah, if you remember. So let's look at how a sync message is sent from this computer, that is 10.1.1.10, this PC, trying to create a 3-way handshake with this server, right? Let's assume they want to do an FTP connection, right? So this IP address of this device is 30.1.1.10, right? So this device knows that it wants to send a port 21 connection, right? So it creates a random port, a random source port, if you remember. If you don't know what we're talking about, I would recommend you go back to our previous videos, go through these ports, right? What ports are, right? So it creates a random source port. It creates a destination port because it knows it wants to connect to port 21, right? And then it looks at the next information that it puts there is layer 3 information. So it puts the IP address, that is 10.1.1.10, that's the source IP address. Then it puts the destination IP address, that's 30.1.1.10, right? Now this data does not change, right? This data does not change until it reaches the end, right? So until it reaches this device, this data does not change at all. What changes is the MAC address information or the layer 2 information, like we discussed earlier, right? That's because switches can only look at layer 2 information. Like layer 2 information is the MAC address. The routers are the only device, or rather in this scenario, router is the only device that can look at layer 3 information. Of course, the computers can look at layer 3 information, right? So looking at the switch and router, switch can only look at layer 2 information. Routers can look at layer 3 information, right? So let's assume this switch does not, it knows its own MAC address, obviously. So it knows that its source MAC address is whatever, 111, right? And it wants to know what's the MAC address of this device. So the computer computes. It looks source IP address and destination IP address, and it realizes immediately, right? If you know how to look at subnetting and if you know how to look at networks, 10.1.1.10, and we're assuming it's /24, these both are from different networks. So the minute the computer realizes that it is not from its own network, it's from a different network, right? Where does it send the data? Right, quite naturally, it has to send that data to the gateway IP address. Now, the most common question I keep getting on these YouTube comments is how or who decides what the gateway IP address is. Firstly, as a network administrator, when you design the network, you give IP address to each of those devices. And now you give an IP address to the device, the router, whichever is the gateway device, you give an IP address. That could be anything. It could be 10.1.1.117, for instance, right? That's a gateway IP address. So it's up to you. You can give any valid IP address in the range in your subnet, right? Now, as a general practice, it is either the first IP address or the last IP address, but there's no hard and fast rule which says it has to be a certain IP address. It could be any IP address in that valid range, right? So in this case, the administrator has set 10.1.1.1 as the gateway IP address. That is this router's F0/0 interface is given this IP address 10.1.1.1. And in this computer, when you configured that computer, you went to, let's say, for instance, you gave a static IP address on this computer. You gave an IP address, you gave a subnet mask of 255.255.255.0, and the next information, which asks for a default gateway, you would have put in this information saying 10.1.1.1. For instance, and let's assume that's the case if it is a static IP address. Now, if it was not through a static IP address, you say your computer had DHCP, the DHCP actually will put that information, right? So it will automatically put that information. So somehow, whether it is static IP address configuration or dynamic DHCP configuration, this computer would be configured with a gateway IP address. That gateway IP address is there for this very scenario when it realizes the communication that it is trying to achieve is with a client or a host on a different network. It has to send that packet or data to the gateway, right? So in this case, the gateway is 10.1.1.1. So this device knows that it has to send the packet or this frame to 10.1.1.1. But then this is the local network transfer, right? So whatever transmission that happens in the local network, the IP address has absolutely no significance. It's only about MAC address. So this computer, right, let's assume that it has not communicated with this device, at least now. The device has just come on, so it has never before communicated with that device. So it has to send an ARP message to ask for the MAC address. So it will send an ARP. What does the ARP contain? It contains the IP address. So it says, hey, who is 10.1.1.1? Please give me your MAC address. Now, since it's a broadcast message, the switch sends out that ARP onto all the ports, right? So all of those devices, including this router, receives that ARP. This device says, I'm not 10.1.1.1, right? It drops it. This device also says, I'm not 10.1.1.1. It drops it. This device, the router, receives that and says, yes, I am 10.1.1.1, and it puts his MAC address, right? This port's MAC address, right? Each port has a different MAC address. So this router puts the MAC address of this port F0/0, sends it out in the ARP reply. The ARP reply goes back to this device. Now this device knows the MAC address. So it puts that MAC address as the destination MAC address, and it sends that frame. Right, before it puts it on the frame, it also puts an FCS or CRC, the cyclic redundancy check. What does cyclic redundancy check means? It's an error checking mechanism where it takes this entire thing, right? It puts this entire thing onto an algorithm. It creates a value, right? Puts that value at the end, right? And it sends, the frame goes through the wire, right? And it reaches this device. Now, when that device receives, it takes that FCS value or CRC value. It does the same algorithm what was done by the sending device and checks if that algorithm results the CRC value. If it does, the data is not corrupt. If it does not, the data is corrupt. Now, what is data corruption? Because data is nothing but zeros and ones, right? And zeros and the way computers work is when there is current or when it's on state, the computer, the receiving device says, okay, I've got a 1. When there's no current, or when they put it off, it's a 0. So it's zeros and ones. Any leakage of current on a physical medium like your Ethernet, right? I'm not saying this is common, but it can happen. You know, if there is a hub, for instance, it corrupts data very, very often. So if there's a corruption where there is a leakage, so ones become 0, zeros become 1, right? Even 1 bit changes, that data is corrupt and FCS or the CRC will not match, and this device has to resend that frame again, right? So once that happens, this device gets this and it looks at the MAC address, right? It looks at the MAC address. It says, it strips that. It says, okay, now layer 3, let's look at the layer 3 information. When it looks at the layer 3 information, it realizes this particular frame has to go to 30.1.1.10. Right? This is where it gets interesting. Previously, when we did this, we said this device, the router, somehow knows where to send this device. That's because because we were talking about switches, I was not really interested to talk about routing. So that's why I said what I said then. Now let's see how it knows what it knows. How does it know? Like for instance, in this case, I have added, let me just put take the pen. Right. So I've added a couple of more links, right? So it has 4 ports in this, right? F0/0, F0/1, 0/2, and 0/3. Now, how does this device know that the network 30.1.1.0/24, right, this particular network, how does it know that it has to send the data through this port, right? It could have very well gone here or here, right? So what happens is routers work with something called as the routing table, right? So routing table is a table that every router has. So it immediately when it has to do a routing decision where to send a particular frame, it looks at its routing table. Whenever any port is connected, like for instance in this case, in this case, F0/0 is connected or configured with the IP address 10.1.1.1. That means it is connected to the 10.1.1.0/24 network, right? Similarly, the F0/1 is configured with the IP address 20.1.1.0/24, right? Because it's configured with 1.1.1. So that means F0/0 is part of the 20.1.1.0/24 network. So these two networks, the 10.1.1.0 and 20.1.1.0 network, this device definitely has to know because it is directly connected to it, right? So this information and this information is default. Now, how does it know about, let's assume 40 and 50. So let's assume F0/2 is connected to 40 and F0/3 is connected to 50. And 30.network is connected to this device. So this device again has a routing table of its own, which says 30. is connected to my interface here, and let's assume this is 0/1, and let's assume this is 0/0, right? So this device says my 0/0 is connected to 20.network, and my 0/1 is connected to 30.network, right? It knows nothing else, and this device by default knows nothing else. It knows only these two information. And if it's connected to 03 and 02 is connected to 40 and 50, let's say it knows these two information, but it doesn't know anything about 30.network. Routing by routing protocol, right, is what tells these devices about those routes that it does not know, right? The mechanism by which these routers communicate with each other is the base of routing, right? So once they communicate, so we will look at it. We have different types. We have static routing or dynamic routing. Static routing is when I go into this device and I put an information there saying if you want to go to 30.1.1.0/24, go through F0/1, right? That's static routing. I can go and put that here. So this packet will come here, it'll go here, it'll go to this device, and then this device will look at it, it'll send here. But with this device will not be able to communicate back to 10.network because the data will come back here to this device, and this device will look at its routing table and it says I know 20, I know 30, but I don't know where 10 is. So I need to go to this device and again put a static route saying, okay, you want to go to 10.network, please send it out on 0/0. So it has to send here, right? So I have to, when you do static routing, the problem is you have to statically go and configure that route up one either way. So going way, so I need to, on this device I need to configure 30.network, and on this device I need to configure the 10.network. Now it's easy when it is 2 router. If you have, let's say, 10 routers, you will have a tough time doing static routing, right? Then we need something called the dynamic routing, right? I think we're getting slightly ahead of our topic. So let's assume. So after this device looks at that packet and says, if you want to go to 30.network, please follow this path, that is F0/1. So it says, okay, fine. It puts the MAC address, source MAC address is BBB, and destination MAC address is CCC. It sends it out. That frame goes to this device. It takes it again, strips this layer 2 information, looks at layer 3 information. It says, okay, 30.1.1.10 is part of the 30.1.1.0 network, which I am connected to, and I know this device. So it says, fine, I'm going to put MAC address, source MAC address, destination MAC address, send it out, and this frame reaches this device. And this process continues. Like I said, this device has to now communicate back to part of the three-way handshake. It has to send that frame back, right? CCNA message. It has to send the CCNA message back to this device. So it comes to this device. This device looks at it. It looks, yeah, obviously when this device gets in, then it strips all that information, and then it looks at all that information, looks at this is a SYN message. It has to send a CCNA, right? So that's how it works. So when this device sends back, this router again looks at that information. It has to somehow learn, right? So you get an idea. This is where router was. I mean, this is where the switch was, which we learned earlier. And now we are looking at the routers, how routers are going to work, right? And that is where routing will come in. So what is routing basically? Let's assume we see such boards throughout our daily life. You know, when we commute, drive through the roads, we have these signs all around, right? So this is when you're approaching a roundabout. It says the first exit takes you to RAF Fairfax. The second exit takes you to the airport. The third exit will continue on M1, M4 south, right? The fourth exit is blocked. Fifth exit will take you to the town center, right? So basically what routing is, it is a way routers make decisions, right? Now this analogy is not absolutely the way routers work, because in this case you as a driver will make a decision where to go, right? But in the case of networks, the devices like the router will make a decision where to send the packets, where to send those frames, right? But then just to understand, a routing is basically creating those routing tables and making those decisions of where to send the data. So there are two types of routing basically, like we discussed, the static routing and the dynamic routing. So static routing is when you have two devices, right? For instance, let's say we have three devices. So let's say this is device 1, this is device 2, and this is device 3, right? And they're connected. So this is connected and this is connected. And this has a network, this has a network. Now, if this network wants to communicate with this network, and let's assume this is the 10.1.1.0, this is the 20.1.1.0, this is the 30.1.1.0, and this is the 40.1.1.0. So every interface of a router should be part of different networks. It could be different subnets, but different networks, right? So if devices from this 10 dot wants to communicate with 40 dot network, this router should know about, right, by default, like we discussed earlier, because this router 1, I'm going to give it a name, router 1, router 2, and router 3, right? Router 1 is connected to 10 dot network and 20 dot network, so it definitely knows about these two networks. It knows nothing else. Router 2 knows only about 20 and 30 because it's connected to 20 and 30 network. Router 3 knows only about 30 and 40 because it's connected to 30 and 40. Now in this case, if I want a communication happening between the 10 dot network and 40 dot network, I need to go to router 1. Tell this router about 30 dot network. I should tell, if you want to reach 30 dot network, please send it out on this interface, right? And I should also go there and tell, if you want to reach 40 dot network, please send it out on this network, right? That's how it is. Similarly, if I go to 40 dot networks, right? Now, if I go to the router 2, Router 2 knows only about 20 and 30, so I need to create two networks. That is, I need to tell 10, if it wants to go to 10, please send it out here. And if it wants to go to 40, please send it out here. So I need to put two routes in router 2. Similarly, in router 3, I need to tell information about route 10.1.1.0 and 20.1.1.0. So these two network I need to tell where to go. That is here. I need to tell that it needs to send out here. And you see how it is. Static routes will initially it's very easy. You can, if it's a small network, it's very easy for you to do it. But as the network becomes bigger and bigger, it will start creating a lot of trouble because it is difficult to manage. You need to add routes everywhere, and you will have problems like this. Let's assume there is a new route now. A static route will always keep sending here because that's how you configured it. But a dynamic routing protocol will automatically recalculate and say, fine, this is our route, but because there is a new route now, I can take this route. So automatically it will update its routing table to say, if you want to go to 40.network, please go through here. That's routing table. So basically, that's how the routing protocols work. So let's look at routing protocols. There are two types of routing protocols: the IGP, or the internal gateway protocols, and the EGP, external gateway protocol, right? IGP protocols are protocols which works with single autonomous system, right? In plain English, that means every router, let's say you're a small organization and you have 5 routers. If you're talking about communication between these routers, we use IGP. If you're talking about routers part of the network, internet, like ISPs, like your ISP, if they have to configure routing protocol to communicate on the internet, they use the EGP, right? So that's the difference between IGP and EGP. IGP, there are 3 popular protocols: the RIP, OSPF, and EIGRP. And your CCNA, latest CCNA curriculum only talks about OSPF and EIGRP. RIP is, I would say, one of the most rudimentary, or one of the most simplest form of routing protocol, and it's one of the most commonly used routing protocol as well. Not much of security. It's very simple, but the latest CCNA curriculum, they have taken that off. But then we will still look at RIP protocol. So I will talk to you all about RIP. I will teach you all RIP because I think it's a good protocol to learn and it gives you a basic understanding, right? We will start from RIP and then we'll go to OSPF and EIGRP. Similarly, external gateway protocol, there are 2: BGP, right, border gateway protocol, and EGP, which is external gateway protocol. Don't confuse, this EGP is classification, this EGP is actually a protocol. So EGP has a protocol called EGP, right? So for our CCNA and for major part, nobody talks about EGP. We're only concerned about BGP. We will look at OSPF and EIGRP. That's part of your curriculum. But we'll also look at RIP. That is, I think, bonus information for going through our network videos, right? So there are 2 types of routing protocols, right? One is called as a distance vector. Another is called as the link state. A distance vector only looks at the distance, right? For instance, if router 1 to router 4, if I want to communicate, there are 2 paths. One is direct path like this, right? Another path is like this: router 1, router 2, router 3, and router 4. If you're talking about distance vector protocols, so routing protocols that uses the distance vector method, it will always take the shortest path. It's called the shortest path first, right? So it takes the shortest path. It doesn't matter whether that is the slowest connection. In this case, this path between R1 and R4, it is a very slow 128 kbps connection, right? Whereas the path through R2, R3 is 100 Mbps, 100 Mbps, 100 Mbps. It's way more faster than the 128 kbps. But protocols, if you're running, for instance, RIP, right? RIP is distance vector, right? So if you're running RIP, which is a distance vector protocol, it will always, on this router 1 table, let's say we have some network here, we have some network here, and let's say this is the 10 dot network and this is the 40 dot network, right? And this example also I'm going to put, so this is the 40 dot network and this is the 10 dot network, right? Now if I put this like this line, it doesn't mean it's just a line. That means that's a network, right? That's one of the shorthand writing. If you're drawing a network diagram, that's how you draw. If you don't want to draw computers by hand, right? So let's assume there are many computers here, and this is a 40 dot network, and this is the 10 dot network. So if the communication between 10 to 40 has to happen, if I want to do static route, I'll come here and I will say statically that if you want to go to 40 dot network, please go through this route. But if I, let's assume, configure RIP, I go to this device R1 and configure RIP, I go to R4 configure RIP, R2 configure RIP, and R3 configure RIP, right? This R1 routing table will automatically say that if you want to go to 40 dot network, please go through this, right? Why? Even when this is faster, it will always choose the shortest path. That is the algorithm. The algorithm is the shortest path first. So it will always look at the shortest path. It has got only one hop, just one hop, and it reaches 40. Take this route. But whereas link state, a protocol like OSPF, right, it will always look at the link state. So it looks at this and it says 128 kbps. That means it's going to be very, very slow. If I go through this, it's going to be a longer path, but because the speeds are much more, it will go like this. So if I go enable OSPF in all the 4 routers, this router R1's routing table will say, if you want to go to 10 dot network, please go through R2, then R3, R4, and then reach here. That's link state. So RIP follows distance vector, OSPF follows link state. We have another routing protocol called EIGRP, and this is a Cisco proprietary routing protocol, right? So if you're talking about Juniper or any other networking devices, you'll never hear about EIGRP. EIGRP is a Cisco domain, right? And it's a very, very beautiful routing protocol. It's much more efficient than both RIP and OSPF. But you cannot use it with anybody else. And since we are part of the Cisco industry now, right, we're talking about Cisco CCNA, we will learn about EIGRP and we will see why EIGRP is very, very good. What's the advantage of EIGRP? EIGRP takes what's good about RIP, or rather what is good about distance vector, and it also looks at what is good about link state, and it has created a hybrid routing protocol, and that is why it is beautiful, and we will look at it a little later in the series, right? So I think we have given enough information about what we are going to look at in the future. In the next video, we will boot up a Cisco router. We will look at different parts. We'll look at the Cisco IOS for a bit. We will have an understanding and we'll see how similar it is from the Cisco switch. So Cisco switch and Cisco router has a similar operating system. So we'll look at the interface. The interface is very, very similar. And maybe I think today is day 18, right? So day 19, day 20, we will look at routing protocols and we will go in depth, learn about RIP, and then future videos we'll start learning about all the 3 routing protocols, and we'll implement those in a small network that we create. We will show you how to configure that in a Cisco router, and we will continue. So thank you so much for coming and joining me today. We will be adding more videos very soon. People keep asking me, is it enough? No, it's not enough. We have to complete this series. The series would have about 60 videos or more, I don't know. So I will tell you when it is right. So until I tell you you're ready for your exams, you're not ready for your exams. So if you're only following our series, that is, if you're looking at other books and stuff, then that's a different story. But if you're following only my series on CCNA, I will tell you when you're ready to take your exams, and we will be finishing this series very soon. We will be adding more and more videos, and we will try to increase the frequency, right? So thank you so much for joining me today. I will see you very, very soon in the next video. Thank you. Bye-bye.